So today we're doing two derivative problems, which of course this is the first of the two. And the idea here is to look at this problem and look at another problem which is very similar to this problem and understand that derivatives can actually be, before they're taken, before we actually take the derivative, we can rewrite these derivative questions in a simpler form such that taking the actual derivative is not as challenging. So looking at this question here, it strikes us, I would say, to use the quotient rule, and that'd probably be a good idea. But of course, doing the quotient rule with this in the denominator, that is, of course, x plus a over x, can be somewhat tedious. And of course, the complexity makes you more apt to make more mistakes, which can ruin the overall result. So our goal, I would say, first and foremost, is to rewrite the denominator of x plus a over x into something more manageable in terms of taking the derivative. So if I were to look at x plus a over x, we would have x plus a over x. So, well, actually, we have x plus a over x. So we can rewrite this as being x x squared plus a, in that I have essentially taken a fraction, multiplied the denominators, and then cross multiplied. And the thing here is that our final, so we can essentially make this logical leap that taking the derivative of this is essentially the same thing as taking the derivative of x over x squared plus a over x, which logically speaking is the same thing as taking the derivative of x over 1 multiplied by x over x squared plus a, which of course is the same thing as taking the derivative of x squared over x squared plus a. And essentially our final, we'd essentially start taking the derivative from this point, which is far more simple than taking the derivative from this point here. And one thing you have to remember is that we could have, in an exam setting, perhaps we could have made these logical deductions one after the other, but we could have went straight to, we essentially could have went straight to this point here by multiplying the numerator and the denominator by x. So essentially what I mean by that, if we take a step back here, is if we had our original problem, which is x over x plus a over x, we could have multiplied the numerator and the denominator by x, which would essentially render us multiplying by an equivalent, because x over x is essentially just 1. So it's not changing the value of the fraction. More so, it is allowing us to do some algebraic manipulation such that we can get rid of the form we find in the denominator. So if we were to do this here, we'd get x squared in the top, and then of course distributing the x to both the x and the a over x, we'd get x squared plus a over x times x, which would of course then cancel out the x's here, so we'd get x squared over x squared plus a, which you'll notice is essentially the same thing that we got through our previous logical deduction in terms of rewriting in different forms. So essentially the thing that you want to remember is that when you're looking at a complex derivative or a complex fraction at any rate, can we in fact express the denominator or the numerator in a simpler form such that it becomes a question that we're perhaps more familiar with. So we're finally tasked with taking the derivative d over dx, that is, of our rewritten form x squared over x squared plus a. And of course, rewriting this again, so we'd have to use the quotient rule, right? But of course, we can probably rewrite this in such a manner where we don't actually have to take the quotient rule. We can instead take we can instead employ the product rule, because of course we are aware of the exponent properties, which state that x or rather 1 over x is equal to x to the negative first power, the reciprocal property here. So we could rewrite this particular derivative as being x squared multiplied by x squared plus a to the negative first power, seeing as 1 over x squared plus a is essentially the same thing as x squared plus a to the negative first power. So now we have to just employ the product rule, which states that we take the derivative of f of x multiplied by the second function g of x, adding that to the derivative of g of x multiplied by f of x. And we then, of course, forego having to deal with a fraction while taking the derivative, because you'll note that the quotient rule essentially has the same thing with a minus in between. But of course, it essentially incorporates the second function, which is of course g of x squared. So we then of course forego having to deal with g of x squared in the denominator, and we also forego having to deal with a negative, which simplifies our problem, seeing as we don't actually have to distribute anything. And so we're then of course taking the addition of f prime g plus g prime f. So it's useful for us to, so we take the derivative, we take d over x of x squared, and that would essentially be multiplied by the second function, which is x squared plus a to the negative first power. And we'd essentially add that to the derivative d over dx of the second function, which is x squared plus a to the negative first power, multiplied by the first function, which is x squared, which is essentially what this formula states. So for the first half here, before on the left-hand side of the addition sign, we'd essentially get 2x multiplied by x squared plus a to the negative first power, added to the derivative of x squared plus a to the negative first power, which we would probably want to do on the side here so that we don't ruin sort of the neatness of the structure that we're laying out here. So essentially we're tasked with taking the derivative of x squared plus a to the negative first power, which would then of course be negative x squared plus a multiplied by the inside here. So this is just an application of the chain rule. So we take the derivative of the inside, which is 2x, and we have the derivative of a. Now a in this particular problem is a constant, so we know that the derivative of a constant is 0, so we just get 0 here, which leaves us with negative 2x within a parentheses of x squared plus a, which is our final derivative for this particular problem here, which is but a subset in our original problem. So really the derivative of x squared plus a to the negative first power is in fact negative 2x and then x squared plus a to the negative second power, because we actually have to decrement the exponent by 1 while we're doing this. So this here we should have actually had a final of negative 2x in parentheses x squared plus a to the negative second power times x squared. So we could rewrite this again as being 2x using the reciprocal property. We could rewrite this as being x squared plus a to the first power, which would render this useless as even writing it. And we would add this to negative 2x to the third, seeing as we actually have to multiply both of these. And we know that the exponent property states that multiplying x to an exponent times x to another exponent is just the exponents added. So we have negative 2x to the third all over x squared plus a to the negative second power. And we could then, of course, rewrite this again as being 2x over x squared plus a minus 2x to the third because essentially our plus and minus here, they sort of merge into being a minus, because we know that plus minus, that's a minus. So we get 2x to the third over x squared plus a to the second power. And then, of course, we take the common denominator between both, and we get x squared plus a squared, right? And essentially, the idea here is now to multiply this by what is missing by what its denominator is missing from the common denominator that we've deduced. So it's actually missing an x squared plus a, so we essentially multiply 2x by x squared plus a, and we subtract from 2x to the third, seeing as this denominator is complete, and we get 2x to the third plus 2ax minus 2x to the third all over x squared plus a squared. And of course, these would cancel out, and we're left with 2ax over x squared plus a squared, which is essentially our final answer. So you can see sort of that we're rewriting things in different forms. And those forms, while they're equivalent to the form we had before, they are simplified, and it is thus not as difficult. So let me go ahead and erase the board here, and we can actually deal with another problem of similar form. So we are thus faced with another problem of similar form, and by now you would note that it's better to actually rewrite this. And so if we were to rewrite the denominator, or actually the numerator, we could express 3 minus 1 over x as simply being 3 minus x to the negative first. And essentially, in doing so, we could rewrite the entire fraction as being 3 minus x to the negative first all over x plus 5. So the quotient rule actually states to take the derivative of f, multiply that by g, subtract that from the derivative of g multiplied by f all over g of x squared. So the derivative of the top here, if we were to sort of look at this, so we would essentially be taking the derivative of 3 minus x to the negative first. And we know that taking the derivative of two functions subtracted or added from each other, or to each other, are actually just the derivatives of the particular functions subtracted. So we would take the derivative of 3 minus that from the derivative of x to the negative first power, and we'd essentially be left with 0, because of course the derivative of a constant is just 0. We'd be left with 0 minus the derivative of x to the negative first power, which is actually just minus 1x to the negative second power, which is actually just, so we'd actually get minus x to the negative second power. And of course, we can then rewrite this as being 0 plus x to the negative second power, which would of course just be 1 over x squared. So really, the derivative of this top function here, which would be f, is 1 over x squared. So we know that f is f prime of x is in fact 1 over x squared. So essentially we take the derivative of f, which we found to be 1 over x squared. So we say that we have 1 over x squared here. And we multiply that by g, which is x plus 5. And we subtract that from, and I'm going to put a bracket just to be safe, we subtract that from the derivative of g, which is in fact, the derivative of g would be the derivative of this function here. So that would just be 1 plus, so the derivative of two functions added together are but the derivatives of the particular functions added. So the derivative of x plus the derivative of 5. So we know that the derivative of x, if we were to do this on the side here, So we would have x to the first power, that would be 1x. And then we decrement the top by 1, so 1 minus 1 would be 0, so we have 0 here. And we know that x to the 0 is in fact 1, so we just get 1 as our final. So we'd have 1 plus the derivative of 5, and we know that the derivative of a constant is 0, so we would have just the derivative of, we just have 1 as our derivative for g. Multiplied, of course, by f, which is 3 minus 1 over x, or really it's 3 minus x to the negative first. But we're going to rewrite this in a form where we can actually perform some algebra. So really, we would just be having the derivative of 3 minus 1 over x here. Now, it's interesting to note that, well, of course, we'd have g over x squared, but it's interesting to note that this is probably not a form we want to deal with. We discussed before that 3 minus 1 over x is actually the same thing as being x, and then we have 3x here minus let's see, so minus 1. So it would be easier for us to just substitute 3x minus 1 into here. So we'd actually be dealing with a whole fraction instead of a whole number minus being, or a fraction being minus from a whole number. So we could actually just say that we have x plus 5 here all over x squared. And then subtracting that from 3x minus 1 over x all over g of x squared. Now, we'd obviously want to distribute the negative here, but we'd want to distribute it in such a way, so there are really two ways we could go about it. Either we could say that we want to change the 3x minus 1 to 3x plus 1, which would not be correct. We just want to change the fraction to negative. So we'd actually have x plus 5 over x squared, as we did before, minus 3x minus 1 over x. So distributing the negative sign, the very act of doing so, just makes the entire fraction negative, multiplied by 1 over gx squared. So looking at this again, we'd want to take the common denominator here, which would be x squared, the highest degree, and we would have x plus 5 here because, of course, the denominator of x plus 5 is not missing anything from the denominator of the LCD or the LCD itself. And we subtract from x multiplied by 3x minus 1, given that the denominator of 3x minus 1 is missing a x as compared to the LCD that we have. So we'd have x plus 5 minus 3x squared minus x all over x squared multiplied by 1 over g of x squared. And we'd have x plus 5 minus 3x squared plus x, seeing as we want to distribute the negative all over x squared, multiplied by 1 over g of x squared. And of course, we would then want to simplify. So we'd have minus 3x squared plus 2x plus 5 all over x squared. And that would essentially be our final answer.